Okay, so now let's look at this equation, 49w double prime plus 112w prime plus 64w equal to 0. So the auxiliary equation is 49r squared plus 112r plus 64 equal to 0. Now, whenever we have a quadratic expression in which the quadratic term and the constant term are perfect squares, which in this case, the 49r squared is the perfect square of 7r, and 64 is the square of 8. So then what we try to see is that if the middle term is 2 times this first base times the second base, so 2 times 7r times 8. And if you see, 2 times 7 is 14, and 14 times 8 is 112. So this does multiply to 112r. So if that happens, then it means that the expression is factorable. And not only is it factorable, but it's a perfect square of this first base plus the second base if the middle term is positive. And if this middle term was negative, then it would be 7r minus 8. Okay, so this whole square equal to 0. So now this is a case where we have repeated roots. R is equal to negative 8 over 7, and the same root repeats twice. We don't have two different roots. So in the repeated root case, we wrote that the general solution is C1 plus C2t e power RT, where R is the repeated root. That was case 2 if you go back and review. And that W is equal to that. In general, it's Y is equal to this, because most equations are Y double prime and Y prime here. So in this case, we have W. So we'll have W equals C1 plus C2t. So that always happens in repeated roots. And then you have E power, and then the repeated root comes here times T. So the root here was negative 8 over 7. So the next example is you have y double prime plus 3y prime equal to 0. But now we have initial conditions also, y of 0 equal to negative 6 and y prime 0 equal to 12. So we start the same way. The auxiliary equation would be r squared plus 3r equal to 0. This factors into r and r plus 3. So r equals 0 and negative 3. So the general solution, in this case, the roots are different. So the general solution is y of t equal, okay, this time we have y, so it'd be y of t equals c1 e to the r1t plus c2 e to the r2t, where r1 is 0, r2 is negative 3. So when you substitute r1 equal to 0, you get e power 0t, which is e power 0, which is 1. So you just get c1. And then when you substitute negative 3 for the r2, you get c2 e power negative 3t. So y prime would be the derivative. So the reason why we are getting y prime is to use the second condition. So this is a second order equation. So we need two conditions to find the two constants. So remember when we did not have the initial conditions, we used to say that the solution of the equation is this and then that, and then we would substitute, and that would be the answer to the problem. But in this case, since we do have initial conditions, so we can't say that this is the solution to the equation. This is the general solution. General solution is the one which involves the constants C1 and C2. And then once we find the constants, then that will be the solution. So when you take the derivative of this, the derivative of C1 is 0 because C1 is a constant. And then the derivative here is C2 e power negative 3t times negative 3. So you get negative 3c2 e power negative 3t. And now the first condition was y of 0 equal to negative 6. So y of 0 is obtained by substituting 0 here. So you get c1 plus c2 e power 0. And that's equal to negative 6. And so this simplifies to c1 plus c2 equals e power c1 plus c2 equal to negative 6. And the second condition was that the derivative as 0 is 12, y prime 0 equals to 12. So substitute 0 in the y prime. So y prime 0 equals negative 3c2 e power negative 3 times 0. That's equal to 12. So this simplifies to negative 3c2 equals to 12. So this gives us c2 equals negative 4. And then we can substitute the value of C2 in this first equation. We can say substituting in 1. We get 1 was this, and substitute C2 equals to -4. And so C1 comes out to be -2. Now we have both the constants. We substitute that in the general solution. So this was the general solution. So C1 is -2 and C2 is -4. -2 minus 4e -3t. Okay.